Now let us discuss what is tolerance stack-up analysis. Tolerance stack-up analysis is stacking the components within available space. All the components in assembly should fit in as required. The thickness should be sufficient as required. So this is what tolerance stack-up analysis, accommodating the component within available space. If you see these images, like these are also kind of stacking the things. See this, a bike having 6 7 people, though there was no space, still it got accommodated over there, right? See this truck, how the things are stacked over there. So stack up analysis is to know within available space, am I able to fit all the components or no. So this is in simple language, that is what tolerance stack up analysis is. Within available space, accommodating the components in assembly, that is what stack up analysis is, that we get to know about that. So that is what tolerance stack up analysis. Tolerance stack-up analysis is the way to find out minimum or maximum gap or interference in a part level or assembly level. So we can get to know whether there are going to be some interferences or no. This is also called as a gap analysis. This tolerance stack-up analysis is also called a gap analysis. Generally, we evaluate minimum and maximum gap and we figure out that it is going to work for us or no. So that is what gap analysis. Using this tool, we can optimize the tolerances. If we are giving too loose tolerance, we can tighten it up as required. And if we are too conservative, giving too tight tolerance, by doing this, we get to know that, okay, need not to have that tight tolerance, so we can loosen it up. So in that way, it can control the machining cost as well. So by doing tolerance stack up analysis, we can control the machining cost as well. That is what tolerance stack up analysis is. Now let us discuss about a case study, that is a came and came guide profile, where tolerances got issues, the dimensioning style got issues, and it costed a lot to the vendor, to the manufacturer. So what was the assembly and what was the drawing is, suppose this is a came guide, a plate having these slots are there, that is a came guide, and this is a protrusion over there. If I look into the side views, this is something like this slot goes there, and this piece is protrusion over there on the surface, and the came has to pass through all the way. And this is the dimensioning style. A chain dimensioning is followed, each in individual these step heights are given over there. So this is the drawing given for this plate and slot dimensioning. And now let us see in the assembly how it is working over there. This is the plate and the came moving over there. If you see, this came is moving over there and it passes through all the way till there. It starts from there and it moves all along there. I cannot explain it functionalities and all, but this is the assembly, suppose, and the chain dimensioning is given over there. Now suppose worst case got manufactured. In worst case, what might happen, that this slot get moves too closer to this protrusion that we discussed. So it may be possible that these are too closer, and when came passes, it moves in the assembly, it goes through that protrusion, and it may be chance that it is too nearby to each other and it gets stuck over there. This gets stuck over there and it's not passing through because of the dimensioning methodology and all, this slot and this thing is too near to each other. So that might be a scenario, and we need to counter this with tolerance stack up analysis. So by doing tolerance stack up analysis before these gets manufactured, we can know the reasons and we can counter that as well. So let us see that. Now let us see that what might be a problem and what we can do. This is the dimensioning style, right? Every feature is dimensioned in a chain. So it may be possible that all these are manufactured on its extreme, like 24 2.47, 3.31, 2.27, 3.39. So if it gets manufactured like that, due to all these tolerances are getting dumped over there, so that is 0.04. That movement, this surface movement will be from mean, it will be 0.04, because all these tolerances are getting dumped and this tolerance is also affecting over there. So to counter that, this is a lot of tolerances are getting dumped, and we can minimize that. We can study, we can do the tolerance stack up analysis, and we will get to know that what is going to happen over there. The came will stuck over there, so we can find it out that, and we can update the drawing in a way. These are all dimensions that is contributing to that gap. We can identify that and we can minimize those dimensions. Instead of giving chain dimensions for all, at least for this surface, what we can do, we can directly dimension from the A's. We can directly dimension from there. We can give these two dimension only. So in a way, what will happen, these two surfaces are directly controlled from a single surface, and this only tolerance that is going to affect it. So in a way, we can improve the dimensioning style by doing tolerance stack up analysis, and we can save the cost. Sometime what may happen that it got manufactured and it may cost in $1 million as well. Suppose this plate is too critical, now it got manufactured but it's not working, so we have to get it manufactured again, and that's a lead time over there. So lots of time gets lost, and that's a cost. Time is a cost over there now. So that is why tolerance stack up analysis is needed. Now let us move to another case study. Let us discuss another case study, that is ceiling plug assembly. Suppose there is assembly like this. It has a thread over there and it has a thread over there. It is going to be assembled, and this is a ceiling slot, means it's for o-ring slot over there, o-ring groove. Now o-ring will be there and it will get assembled. There is a thread connections over there. So this is the assembly. Now let us see why we need tolerance stack up analysis in this case. See this, this is a critical gap for us, that is a extrusion gap, and we need to maintain it critically particular value. Extrusion gap should not be more and should not be too tight for the sealing requirements. So this is the dimensioning given on the drawing. Now this is thread dimension given over there. This is thread dimension for that that may be acme thread or whatever that thread is, and then we are mostly interested in these two dimensions, how this is going to be assembled and what will happen if we do not do tolerance stack up analysis over there. So we need tolerance stack up analysis over there. Let's see why. Now let us see what is going to happen with that ceiling plug assembly. So here, as we know, we are mostly interested in these two dimensions, right? What we can do, we can calculate MMC of plug and MMC of the ceiling ID. Both is almost there. In first go, you will see in a worst case case it is going to be same. There will be at least some extrusion gap whenever it gets manufactured at its mean dimension. So it seems okay in first go. But you know, we haven't considered the effect of these run out tolerances. These run out tolerances we haven't considered. This run out tolerance, suppose the form is perfect, that circularity is perfect over there, so it is equivalent to that position tolerance. If it is perfectly round, this run out is equivalent to position tolerance. So in that case, if both are not that aligned with the axis of that thread or the datum A, so that will create a problem in assembly, and that will also need to include in tolerance stack up analysis. After that, we can analyze what will be the minimum or maximum extrusion gap. So in such cases as well, we need tolerance stack up analysis. Simple calculation will not work over. As we have seen a couple of case studies now why we need tolerance stack up analysis, let us move towards further learning steps to be followed in tolerance stack up analysis, the methodology, the loop diagram, stack up table and all. But before starting that, let us learn how we decide a particular tolerance value. That remains major question in our mind. So let us discuss how we can decide a particular tolerance value, and then we will move towards main course. Thank you.